So an idea that we should return to real quick before moving on. So a thing we should dig into a little bit before we move on is this idea of the substantial derivative. Because an interesting thing shows up when we start looking at unsteady effects. This first term, with respect to time, the first derivative is with respect to time, and we often call this the local or the time derivative. This business over here, though, the other terms, the u d by dx, v d by dy, w d by dz, these show up and are called the convective derivative. And what's interesting about them is that they showed up as a result of the chain rule, and they have to do with the value moving from one location to another. So a property or whatever being taken from one location in the flow to another. So that's the value of the thing when we move from one location to another. I go from one place to another and the velocity changes. I go to one place to another and the density changes, whatever it is. This is associated with moving around in our flow field. On the other hand, this term here is called the local because it happens at a single place. And what's interesting is that it can be equal to 0 when it's a steady flow, for steady, right? With any steady state, any steady flow, we get rid of time derivatives. It's not equal to 0 for an unsteady. And the key idea here is that this is the value at a point. So real quickly, if we look at a nozzle, this might become a bit more obvious what we're talking about. So draw this out real quick. If we have some flow coming in here at V1 and some flow leaving here at V2, we can think about the fact that if it's steady, mass conservation would look something like this. dm dt is equal to rho v1 a1 minus rho v2 a2. And so if it's steady, we get rid of this time derivative because it's steady. And that tells us then that v1 a1 is equal to v2 a2. In other words, velocity increases as we go from 1 to 2, even in a steady flow. And so there's this counterintuitive idea that a steady flow can accelerate. And it can. That's convective acceleration. And so we come back up here, these convective terms are what are responding when we have steady flow that accelerates. And so another way you could think of this is that this d by dt term, the velocity at any location in our pipe would change, say, if we opened and closed a valve that changed the mass flow rate. That would be an unsteady effect. So we could make V1 vary in time by opening and closing some valve. On the other hand, even when it's steady, V1 and V2 are different because of the area change, and that's that convective term.